Good morning, friends. I am Muskan from BSc Chemistry Honors final year. Today we are going to discuss Raman spectra. It is a special type of spectroscopy which deals not with the absorption of electromagnetic radiations but deals with the scattering of light by the molecules. It is observed that when a substance, which may be gaseous, liquid, or even solid, is irradiated with electromagnetic monochromatic light of definite frequency mu, a small fraction of light is scattered. Rayleigh found that if the scattered light is observed at right angle to the direction of incident light, the scattered light is found to have the same frequency as that of incident light. This type of scattering is called Rayleigh scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance, gaseous, liquid, or solid, is irradiated with monochromatic light of definite frequency mu, the light scattered at right angle to the incident light contains lines not only of the incident frequency but also of the lower frequency and sometime of higher frequency as well. The lines with lower frequency are called Stokes line, whereas lines with higher frequency are called anti-Stokes line. Raman further observed that the difference between the frequency of incident light and that of the particular scattered line was constant, depending only upon the nature of substance being irradiated, and was completely independent of the frequency of incident light. If mu I is the frequency of incident light and mu s is that of particular scattered line, the difference del nu mu is equal to mu I minus mu s is called Raman frequency or Raman shift. Thus, the Raman frequency observed for a particular substance are characteristics of that substance. The various observations thus made by Raman constitute what is called Raman effect, and the spectrum observed is called Raman spectrum. Thus, in a simple way, Raman spectrum may be represented as shown in figure 3.29. Explanation for observing Rayleigh lines and Raman lines. When incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collision means that the colliding particles will return with the same energy. Thus, the scattered photon has the same frequency as that of the incident photon. This explains Rayleigh scattering and Rayleigh line. However, if the collision is inelastic, still the law of conservation of energy will hold good. That is, total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that scattered photon has lower energy and hence lower frequency than that of the incident photon. This explains the occurrence of Stokes line. Alternatively, some energy may be transferred from the incident photon of the molecule so that the scattered photon has higher energy and hence higher frequency than that of the incident light. This explains the occurrence of anti-Stokes line. This explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is observed by the molecule and it gets excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as observed, and thus we have Rayleigh scattering. However, in most of the cases, the excited molecule does not return to the original level. It may return to a higher level than the original level, thereby emitting less energy than observed. This explains the occurrence of Stokes line. Thus, a part of energy of incident photon remain absorbed by the molecule so that molecules have higher energy than before. Alternatively, the excited molecule may return to a level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes line. In this case, the molecule has less energy than before. The different cases may be represented diagrammatically as shown in figure 3.30. Levels have been shown equally spaced just for the sake of convenience. Polarizability of molecules and Raman spectra. The Raman effect arises on account of the polarization, means distortion of the electron cloud of the scattering molecule that is caused by the electric vector of electromagnetic radiation. The induced dipole moment mu depends upon the strength of the electric field and the nature of the molecules. We write mu is equal to alpha E, where the quantity alpha depends upon the nature of the molecules and is called polarizability of the molecule. Thus, polarizability is the ratio of induced dipole moment to the strength of electric field. In case of atoms or spherical symmetrical molecules such as methane, SF6, etc., same polarizability is induced whatever be the direction of applied electric field. They are said to have isotropically polarizable. Such molecules are said to be isotropic molecules. In case of R diatomic molecules, homonuclear or heteronuclear or non-spherical molecules, non-spherical rotators, the polarizability depends upon the direction of electric field. For example, in case of S2 molecule, the distortion produced is more when the electric field is applied parallel to the bond than when it is applied perpendicular to it. Such molecules are therefore said to be anisotropically polarizable. Types of molecules showing rotational Raman spectra. A molecule scattered light because it is polarizable. Hence, the gross selection rule for a molecules to have a rotational Raman spectrum is that the polarizability of the molecule must be anisotropic. That is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of electric field. Hence, all the diatomic molecules, linear molecules or non-spherical molecules give Raman spectra, that is, they have rotationally Raman active. On the other hand, spherical symmetrical molecules such as methane, SF6, etc. don't give rotational Raman spectrum, that is, they are rotationally Raman inactive. These molecules are also rotationally microwave inactive. In fact, this is one of the reasons for importance of rotational Raman spectroscopy over infrared spectroscopy, because the latter requires the molecules must have a permanent dipole moment, whereas the former only requires that polarizability of the molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration or rotation. It is the sum of two parts, which is first is equilibrium polarizability, that is the polarizability when the atoms of the molecules are in their equilibrium position. Second is sum of the polarizability of the molecule due to various rotational and vibrational motions. Each term depend upon the frequency of the rotation or vibration. Thus, alpha is equal to alpha naught plus summation of change in alpha in the nth rotational and vibrational modes upon change in the maximum displacement of the atom in volts multiplied by Rn cos 2 pi mu n t, where alpha n is the polarizability associated with the nth rotational and vibrational mode, and Rn is the maximum displacement of the atom involved. Further, electric vector of electromagnetic radiations vary with the time in a sinusoidal manner, as E is equal to E naught cos 2 pi mu naught t. Substituting the value of alpha and E from equation 2 and 3 in equation 1, we get mu is equal to E naught alpha naught cos 2 pi mu naught t plus summation of change in alpha n upon change in Rn with respect to Rn multiplied by Rn cos 2 pi omega naught t cos 2 pi omega n t. By applying the mathematical relation cos A cos B is equal to 1 by 2 cos summation of AB plus cos difference of AB. Thus, we get the expression mu is equal to E naught alpha naught cos 2 pi mu naught t plus half of E naught summation of del alpha n with respect to the change in displacement into Rn multiplied by cos 2 pi mu naught minus mu n t plus cos 2 pi mu naught plus mu n t. This expression consists of three terms. The first term has frequency of incident radiation and represent Rayleigh scattering. The second term contains mu naught minus mu 1 and represent Stokes lines, whereas the third term contains mu naught plus mu 1 and represent anti-Stokes lines. Quantum theory of pure rotational Raman spectra of diatomic molecules. The selection rule for pure rotational Raman spectra of diatomic molecules are del J is equal to 0 plus minus 2. The selection rule del J is equal to 0 corresponding to Rayleigh scattering, whereas the selection rule del J plus minus 2 gives rise to Raman's lines as explained below. We know that the energy of rotational level in terms of wave number with quantum number J is given by wave number is equal to bjj plus 1. When a transition takes place from a lower rotational level with quantum number J to a higher rotational level with quantum number J dash, the energy absorbed in terms of wave number will be change in wave number is equal to bj dash j plus 1 minus bj into j plus 1. For the selection rule, del j is equal to plus 2, that is j dash minus j is equal to 2, or j dash is equal to j plus 2. We get del b bar change in frequency is equal to b 4j plus 6. Again, for the selection rule, del j is equal to minus 2 means j dash minus j is equal to minus 2, j is equal to j dash plus 2. We get change in wave number, energy absorbed in terms of wave number will be minus b into 4j dash plus 6, where j dash is equal to 0, 1, 2, 3. Combining the result of equation 3 and 4, the wave number of the line obtained in the Raman spectrum will be given by mu bar is equal to mu I bar plus change in wave number, mu is equal to mu I bar plus minus b 4j plus 6, where j is equal to 0, 1, 2, 3 and so on up to infinity. Hence, here mu I represents the wave number of Rayleigh line, plus sign gives higher lines with the higher wave number and called anti-Stokes lines, and minus sign give lines with the lower wave number and called Stokes line. From equation 5, it may be seen that for j is equal to 0, mu is equal to mu I plus minus 6b, that is first Stokes and anti-Stokes line will be at the separation of 6b from the Rayleigh line. Further putting j is equal to 1, 2, 3 and so on, the separation between any two adjacent stroke line or any two adjacent anti-stroke line will be 4b. Thus, the pure rotational Raman spectrum expected for a diatomic molecule may be represented as shown in figure 3.32. Intensity of the lines of the pure rotational Raman spectra. As explained earlier, the intensity of the line depends upon the population of the initial level from where the molecules are excited or de-excited to the final level. Since the population of rotational energy level is shown in figure 3.20, therefore, the intensity of strokes and anti-strokes line vary in similar manner. Application of pure rotational Raman spectra. From the pure rotational Raman spectra, noting the separation between the lines, the value of B can be obtained, from which the moment of inertia and the bond length of the diatomic molecules can be calculated as explained below. As we know that B is equal to h upon 8 pi square IC. By putting the value of B, we can easily calculate the value of I. Quantum theory of rotational vibrational Raman spectra of diatomic molecule. For large molecules, the line obtained due to rotational transition are so weak that they are beyond resolution. Hence, we have pure vibrational Raman spectra for which the selection rules are same as for pure vibrational spectra discussed earlier. That is, change in mu is equal to plus minus 1. Vibrational change in vibrational quantum number is equal to plus minus 1, plus minus 2 and so on. However, in case of diatomic gaseous molecules, the resolution of rotational fine structure is sufficient and can be studied. Thus, diatomic gaseous molecule give rotational vibrational Raman spectra, which can be explained as follow. The selection rule for the transition are: change in vibrational quantum number is equal to plus minus 1 and change in rotational quantum number is equal to 0 plus minus 2. However, at room temperature, as most of the molecules are in lowest vibrational level, V is equal to 0. Therefore, the significant vibrational transition is from V is equal to 0 to V is equal to 1, called fundamental vibrational transition. Restriction ourselves to these vibration transition only. The result obtained are as follow. For del J is equal to 0, change in the wave number is equal to mu e 1 minus 2 xe, where xe is the anharmonicity constant. For del J is equal to plus 2, change in mu bar is equal to omega e 1 minus 2 xe plus b 4j plus 6, called S branch. For del J is equal to minus 2, change in mu bar is equal to omega e 1 minus 2 xe minus b 4j dash plus 6, called Q branch, representing the value of Q as O branches by change in wave number Q, S and O respectively. The wave number for the exciting radiation by Vi. The wave number of Stokes line will be as follows. We have considered the case for del V is equal to plus 1, which represents Stokes line. The anti-Stokes lines for those for which del V is equal to minus 1. Thus, they are usually weak because very few molecules are in excited vibrational state initially. The rotational transition accompanying the vibrational transition from V is equal to 0 is equal to V is equal to 1, and the rotational and vibrational Raman spectrum obtained may be represented as shown in figure 3.32. Advantages of Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as brief explained below. Since Raman frequencies are independent of the frequencies of the incident radiations, hence by suitably adjusting the frequency of incident radiation, Raman spectra can be obtained in the visible spectrum range, where they are where they can be easily observed rather than the more difficult infrared range. Raman spectra can be obtained even for molecules such as O2, N2, Cl2, etc., which have no permanent dipole moment. Such a study has not been possible by infrared spectroscopy. Raman spectra can be obtained not only for gases but even for liquids and solids, whereas infrared spectra for liquids and solids are quite diffuse. Because of ease with which the Raman spectra can be studied, the molecular structure of a large number of compounds has been determined by Raman spectroscopy. However, infrared method still continues to remain popular. Experimental arrangement for Raman spectra. The experimental arrangement for observing Raman spectra is shown in figure 3.33. In experimental arrangement apparatus for obtaining Raman spectra, first we take mercury vapor lamp from which lights, electromagnetic radiation or lights will be emitted, and then they are scattered on the slit, and then from these slits then they fall on the concave lens and through prism, and then after that they strike on the photographic plate. On photographic plate we may get their spectra. The fraction of light scattered is so low that normally very weak Raman lines are observed. Hence, to detect these lines, it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamps were used, which gave an intense monochromatic radiation of wavelength 4358 angstrom, means 435.8 nanometer. However, with the development of lasers, which are very powerful source of monochromatic radiations, Raman spectroscopy has been greatly revolutionized. Thank you.